So, hello students, let us continue from where we stopped in the previous lectures. In the previous lectures, we had seen how to develop our equilibrium equations for bar and beam elements, starting from the fundamentals by applying unit deformations in different directions. We got the equilibrium equations, and we have seen the local coordinate system and then global coordinate system and so on. And now in this lecture, let us go a little bit more mathematical. Let us look at the energy methods for deriving our equilibrium equations, and also look at the principle of stationary potential energy that gives us a very good platform for doing lot of mathematical analysis. See, in this process, we are going to look at only the conservative systems. A conservative system is a system in which the work done does not depend on the path. Say for example, let us say we move the load from point A to point B, and we could move it along the least length direction directly AB, a straight line path, or along the curved path 1 or along curved path 2. Whatever path that you take, the work done is exactly the same. That is the load multiplied by the least distance, and so those systems are called as conservative systems. And you might ask why we cannot consider the path dependence. That is a different thing, because that requires different mathematical formulation, but for now we will only look at this. The work done is independent of the path taken, and if you consider some other methods, maybe it is possible. Okay. So, and already we have seen the virtual work calculation in lecture 4, where we had derived a transformation matrix for the bar element based on the virtual work principle. Like virtual work done, whether you calculate in the local coordinate system or in the global coordinate system, both are the same, and through that we have got k global is lambda transpose k element times lambda, and there also we had calculated the work done, but we did not give any importance to the path taken and so on. But this is the assumption that we make. We consider only the conservative systems where the work done does not depend on the path. Let us look at one of the oldest principles, the virtual work principle. So, if any admissible virtual displacement field is applied on a system and the external and internal virtual works are equal, the system is said to be in equilibrium. Let us say that we have a spring under a load of P, and it is subjected to an elongation of U. On top of this, let us say we give some virtual displacement D, and the internal force within the spring is k times U, right, and the external force is P, and let us assume, let us apply a virtual displacement of delta on the system, and the internal work done is the force in the spring multiplied by D, okay, ku times delta. That should be exactly equal to the external work done by the applied force, that is P times delta. So, if you cancel out delta both from the left hand side and the right hand side, we are left with k times U is P. That is our familiar equation, stiffness times displacement is equal to P, the load. Okay. And so, this is what we have seen for one dimensional elements, and in fact even the spring is a one dimensional element. Okay. And let us look at the same principle, but from a different point of view, the principle of stationary potential energy. Actually, it is it's very easy to imagine that when you have a system under equilibrium, if you move a little bit, the potential energy does not change. I will illustrate that a bit later, but let us look at the statement of this principle. Say, among all admissible configurations of a conservative system, those that satisfy the equations of equilibrium make the potential energy stationary with respect to small admissible variations of displacement. See, the potential energy is constant when we apply some small deformations. Like for example, you take some object and keep it at some height. If you move it a little bit, like apply some deformation, there is some change in the potential energy. So that means that this is not a stable thing. But then say you keep it on a surface like this and move it a little bit to the left or the right, and its potential energy is not changing with respect to my hand or to the surface on which it is resting. So we can say that that is the most stable system. And so this mathematically we can pose this problem so that we can derive some useful relations. So let us take the same spring K and gradually apply some displacement of delta, okay? And let us say there is a load of P, and the total potential energy is pi is equal to U plus omega, where U is the strain energy of the system, and that we can calculate is the average force, because the delta is starting from 0 to delta during this application of this deformation. So the average force is K delta by 2, and that multiplied by delta is your average strain energy, that is 1/2 K delta square, okay? And then omega is the loss of potential energy of the external load. And actually, okay, I should have had this, okay, I will come to this later. Let us say while moving through a distance of delta, the load has lost its potential by an amount of P delta. So we can say the omega is the loss in potential as minus P times delta, because by that much it has lost the potential. Like for example, say if this object is at this height, it has got so much of potential energy, but if I move it, then it has lost that much potential energy to do the work, okay? So our total potential is 1/2 K delta square minus P delta, right? And the principle states that any small disturbance in the total potential with respect to delta should be 0 for the system to be in equilibrium. So mathematically we can say that dou pi by dou delta is 0 for stationarity, and so if you differentiate this, we get K times delta minus P is 0, or K times delta is P, where K is our stiffness, delta is the deformation, that is equal to load P, okay? And so actually this is what we obtained earlier, and we can actually illustrate this with a simple example that we must have, all of you must have studied in your first year mechanics course. Let us say you have a marble in a round container, and the most stable, like if you drop a marble here, it will just go on rolling and rolling until it comes to the bottom, and it is not stable here because it can roll. Or we can say that as you move it, its potential energy is changing. But imagine the same marble at the bottom of this bowl, and just move it a little bit to the left or to the right, its energy is not changing, its potential energy is not changing. So, we can say that that is the most stable position for the marble with respect to the bowl. Okay? And that is what is meant by the statement when we say that among all the admissible deformation states, those that satisfy the equations of equilibrium make the potential energy stationary. So, the potential energy, if it remains stationary, then we can say that the system is in equilibrium or stationary. Okay? So, we can apply this for all our problems, whatever we have come across, and let us apply that to a multi-degree of freedom system. Let us say we have two springs K1 and K2 and three deformations delta 1, delta 2 and delta 3 and three external loads P1, P2 and P3, and we need to first estimate the total potential of the system, internal energy of the system, that is the energy in spring K1 and energy in spring K2. So, the energy in spring K1 is the 1/2 K1 delta 2 minus delta 1 whole square. Okay? And same thing, the potential energy of spring 2 is 1/2 K2 delta 3 minus delta 2 whole square. Okay? And delta 2 minus delta 1 is the relative deformation. Only when you have a relative deformation, the spring will get strained. So, if delta 2 and delta 1 are the same, then there will not be any strain developed in the spring or the force. Okay? So, we are more interested in the relative deformation, and previously we said it is only delta because one end is fixed. So, whatever deformation that you apply to the front end, that is the relative deformation that is caused in the spring. Okay? So, our total potential pi is the potential energy in spring 1 plus spring 2 minus the loss of potential of P1, P2 and P3. So, the total potential is 1/2 K1 delta 2 minus delta 1 whole square plus 1/2 K2 delta 3 minus delta 2 whole square minus P1 delta 1 minus P2 delta 2 minus P3 delta 3, right. And so, we can take this total potential and differentiate with respect to different degrees of freedom. Delta 1, delta 2 and delta 3 are the different degrees of freedom. So, we take a differential of this pi, and if it is 0, then we can say that our system is stationary or in equilibrium. And so, by differentiating with different degrees of freedom, we get sufficient number of equations, simultaneous equations for solving for our nodal unknowns, displacements. So, dou pi by dou delta 1 will give you this, and we get the first equation K1 delta 1 minus K1 delta 2 is P1, right. It is actually, this is similar to what we had seen earlier. We applied unit deformations and then tried to find the corresponding forces. So, if I apply unit deformation at delta 1, the force will be developed at this node or at this degree of freedom and at this degree of freedom. The force is not developed at this degree of freedom because it is not connected. So, that is what we see here, delta 3 is not in this equation. Okay? And then when we differentiate this with respect to delta 2, we get an equation in terms of all the three degrees of freedom, delta 1, delta 2 and delta 3. That is because the delta 2 is connected to both delta 3 and the delta 1. So, if you apply some deformation delta 2, there will be a force developed in this at this degree of freedom and this degree of freedom, and also at this same, at its own degree of freedom. Okay? And so, that is minus k1 delta 1 plus k1 plus k2 delta 2 minus k2 delta 3. And similarly, if you differentiate with respect to delta 3, we get only in terms of delta 2 and delta 3 because delta 3 is not connected to delta 1, right. So, if you express these three equations in the form of matrix, you will get like this: k1 minus k1 0 minus k1, k1 plus k2 minus k2 0 minus k2 k2 delta 1 delta 2 delta 3, that is equal to p1 p2 and p3, right. And we see this assembled stiffness matrix is symmetric because the upper diagonal terms are equal to the lower diagonal terms, and then it is banded. Actually, there is a 0 here, there is a 0 here. So, we have a small band around which we have non-zero terms, and the same equation we have seen earlier even when we derived these equilibrium equations by using the fundamental definition for the stiffness. Okay. So, let us slightly modify this and let us apply some deformation, the boundary condition. So, actually this equation, it is not obvious, but the determinant of this equation, this matrix is 0. So, we will not be able to solve for the deformations as delta is equal to k inverse p, because your determinant is 0, and so we need to apply some boundary condition, and for that we have seen two methods. One is the exact method and the other is the boundary spring method. And let us say that let us not bother about applying the boundary conditions, but right now itself let us say you want to apply some constraint that this particular node does not move, delta 1 is 0. Then the potential energy in k1 will be 1/2 k1 delta 2 square, because delta 2 itself is the relative deformation. So, if not let us say if it is not 0, but let us say some 0.1 or something. So, the relative deformation in this spring will be delta 2 minus 0.1, okay. And we are not using the delta 1 because it is not a variable anymore, it is a fixed value at 0 or 0.1 or something. Then the energy in spring 2 is 1/2 k2 delta 3 minus delta 2 whole square, okay. And so, once again we can differentiate this with respect to different degrees of freedom, okay. And so, our dou pi by dou delta 2, delta 1 is not a variable anymore, like actually p1 delta 1 you can set it to 0 because it's known quantity. And so, our dou pi by dou delta 2 and then dou pi by dou delta 3 will give us some other equation, and now we get only a 2 by 2 equation in terms of delta 2 and delta 3 and p2 and p3. And this matrix has got an inverse because its determinant is not 0, okay. And so, directly we were able to get our equilibrium equations without needing to modify the equations for a fixed degree of freedom. And now let us apply this principle to two-dimensional bar element. Let us consider a bar element with two nodes, node 1 and node 2, and the deformations are u1, v1, u2, v2, and then the forces are px1, py1, px2, py2, and the axial deformation is u2 minus u1 times cosine alpha plus v2 minus v1 sin alpha, and delta square is this whole thing, okay. And our potential equation for the system pi can be 1/2 k delta square minus px1 u1 py1 v1 minus px2 u2 minus py2 v2, right? And so with respect to different degrees of freedom u1, v1, u2, v2, we can differentiate and set it to 0, and we will get our equilibrium equations. So, our dou pi by dou u1 will give you this equation is actually this, and then if you simplify it, you will get like this, and then similarly dou pi by dou v1 will give you this equation, and by taking derivatives with respect to u2 and v2, we get two more equations, and then once you assemble all the equilibrium equations, you will get an equation, a matrix that is very similar to what we had seen earlier. By doing the lambda transpose k lambda, we got this, or by directly applying the unit deformations in the global coordinates, we got similar matrix. So, this k multiplied by u is equal to p, and we can actually, it's a general procedure that we can apply for any problem, but only thing is, if we do like this, we have to do hand calculations. We cannot use any of our matrix methods. Okay, but anyway, let's apply this for some problems, so that we can go through the hand calculations and understand it better. And let's apply this stationary potential energy method to the Truss problem that we had solved in lecture number 4. Okay, and we'll see two cases. The first one is for the same data that was given, and the second one is along with some settlement on the right hand side support. Okay. This was the structure that was given. It has 3 nodes, node 1, node 2, node 3, and 3 elements 1, 2 and 3, and element 1 is connected between nodes 1 and 2, and element 2 is connected between nodes 2 and 3, and element 3 is connected between nodes 1 and 3, and the direction of the element is from node 1 to node 2. So, we get this alpha, and these are the coordinates. Node 1 is at origin 0, 0, node 2 is at 2.5 and 4.333, node 3 is at x is equal to 5 and y is 0. Okay. And for these 3 elements, we have 3 different alphas depending on their orientation, and then we have this cosine alpha and sine alpha. And unlike the previous case, let us not number the fixed degrees of freedom. Okay, let us assign 0 to the fixed degrees of freedom. At node 1, both x and y direction displacements are constrained, so 0, 0. At node 2, we have the degrees of freedom 1 and 2. Let us call them as d1 and d2. Node 3, the degree of freedom along the x-axis is free, that is active degree of freedom d3, and then let us say that along y-axis it is fixed 0 because it is on roller. Okay. And so, the connected degrees of freedom are like this 1, 2, 1, 2, 3, 0, 0, 3, 0 and so on. Okay. And we have deleted all the fixed degrees of freedom and numbered only the active degrees of freedom that are free to deform either in the x-axis or along the y-axis. So, we have totally 3 active degrees of freedom, and the alpha for each element is obtained based on the node numbering scheme that we have adopted, and the energy for the entire structure can be evaluated in terms of our delta axial deformation u2 minus u1 cosine alpha plus v2 minus v1 sin alpha. This is the generic equation, and particular for each of these elements we can get your relative deformation delta. Okay. And so, for element 1 it is connected between node 2 and node 1, and node 2 it has free degrees of freedom d1 and d2, whereas node 1 is fixed. So our delta 1 is d1 minus 0 times cosine alpha, that is x direction displacement is d1 times cosine alpha, y direction displacement v2 is d2 times sine alpha, and the cosine alpha is 0.5 and the sine alpha is 0.866 for element 1. So our delta 1 is this, and our delta 2 is actually connected between node 2 and node 3. Okay, and node 1 is node 2 and node 2 is 3, and at node 3 we have d3 along x axis, and along y axis it is fixed 0. So our delta 2, the relative deformation in element 2 is d3 minus d1 that times cosine alpha, that is the relative x direction displacement, plus 0 minus d2 sine alpha, that is the 0 is the displacement at node 3 in the y direction, d2 is the y direction displacement at node 2 sine alpha, and it just so happens that sine alpha is minus 0.866 for this element 2. So this is the relative displacement in element 2, and delta 3 is d3 minus 0 because the left hand side is fixed. So d3 times cosine alpha, that is simply d3 because alpha is 0 for this horizontal element. Okay. And so our total potential is 1 half k delta 1 square plus 1 half k delta 2 square plus 1 half k delta 3 square minus a load of 100 applied at in x direction at node 2, the deformation is d1. Okay. So this is your total potential. Sorry, I think the total potential is this, and now we can take derivatives with respect to d1, d2 and d3. So if you take if you differentiate pi with respect to d1, you get this 0.5 k d1 minus 0.25 k d3 is 0, and it's 100. And similarly, differentiation with respect to d2, we have this equation, and then differentiation with respect to d3, we will get one more equation. So these are the three equilibrium equations that we have, and we can assemble them, or we can just put them in a matrix form like this. So k is 10,000, 0.5, 0 minus 0.25, d1, d2, d3 is 100, and then that's actually, see, this is 0.5 times 10,000 is 5,000 minus 2,500 because 0.25 and k is 10,000 and so on. Okay. So it is and once you get this, the solution is very simple, and in fact if you see, this is the same equation that we got earlier in lecture number 4 by deleting rows and columns of 1, 2 and 6, because these 3 degrees of freedom are fixed, and by deleting those corresponding rows and columns, we were left with this, and we can invert this matrix and get our d1, d2, d3. Okay. That was what was done in lecture 4. Okay. And now let us consider the influence of settlement at right hand support. See, the support at 3, it is calculated that it will settle down by 50 millimeters. This deformation in the vertical direction is minus 0.05. It is the same data, and so this was the assembled stiffness matrix and then the load vector for that structure. Okay, we had done this by hand calculations, and this is what we have, a 6 by 6 matrix. Then out of this, our the first and second degrees of freedom are fixed. So we can delete the first row, second row, first column, second column, and keep the last one, because the sixth row, because we need that to apply a displacement of minus 0.05. Okay. So in U4, that is in the degree of freedom, y direction degree of freedom at node 3, we want to apply a displacement of minus 0.05. So here we know this stiffness coefficient, and that stiffness coefficient multiplied by this U4 is a known quantity. So we can send it to the right hand side. Okay. And this 10,000 times 0.433 times minus 0.05, and you send it to the right hand side, you will get, and since you already have a load of 100, you add it. Then in the second row also we have this quantity, and minus and minus is positive on this left hand side. When it goes to the right side, we get a minus 375. And the third row also the same thing, minus 216.5. And then the fourth row is actually, it's a trivial row, trivial equation, because U4 is a minus 0.05, nothing else. Okay. And by solving this, we get U1 of 0.0657, and U2 is minus 0.0264, and U3 is 0.005, and U4 is minus 0.05. That is what was applied. And we can do the same problem by defining our relative displacements, and we are saying that on the right hand side, the support settles by an amount of 0.05 meters or 50 millimeters. Okay. So delta 1 is for the element 1 connected between node 1 and node 2, and there is no change in this, so it is the same. And delta 2, d3 minus d1, is the relative deformation in the x-axis, along the x-axis, multiplied by cosine alpha. And then at node 3, the displacement is minus 0.05, and at node 2 it is d2. So this is our relative deformation multiplied by sine alpha, and sine alpha is minus 0.866. So if you substitute that, you get this. And in fact, the relative deformation is d2 plus 0.05, because we are taking the unknown displacements initial in the positive direction. D2 is in the along the positive y direction, whereas 0.05 is in the negative y direction. So the relative deformation is d2 plus 0.05, and delta 3, the relative deformation in element 3, that's on the horizontal element, is just simply d3 cosine alpha, because it's coinciding with the x-axis, and there is no effect of settlement on element 3 and element 1, because they are not directly connected. Okay. And element 3, it is connected, but then it is a horizontal element, whereas the settlement is in the vertical direction. So now once you have this delta 1, delta 2, delta 3, we can form our total potential energy equation, and then take differentiation with respect to delta 1, delta 2 and delta 3, and get our equilibrium equations. So let us see that pi is u plus omega, okay, and delta 1, delta 2, delta 3, we have already seen that. Okay. And actually I think there is a small mistake. Just 1 minute, I think I made a mistake here. Okay, yeah, now it's correct. I forgot to do the square for the entire thing. Okay. plus d3 square, this is correct. And now we can differentiate this with respect to d1, d2 and d3, and you get a messy equation, but then you have to do it by pen and paper method so that you can get it correctly, and I have done that. I've got 3 equations, equation 1, 2 and 3, okay, by differentiation, and then by simplification we get these 3 equations, and then in a matrix form these are the equations d1, d2, d3, and this is exactly same as what we had earlier. Okay. So it is so we see that even by this stationary potential energy method, we could apply a known displacement and then get our governing equations. And if you solve it, if you solve this system, you will get the same displacements that we got earlier. Okay. So here is the tabulated nodal displacements. This is x direction displacement and y direction displacement. This is without right hand side support settlement, whereas this is with a settlement of 50 mm. And if you graphically look at it, this red lines are the original mesh, they represent the original mesh, and then this green lines are the deformed mesh. And you see this actually it has undergone the structure has undergone a rigid body rotation. That's because our node 1 is fixed on a hinge, so we can actually rotate the whole thing, and the right hand side has settled by 50 millimeters, so the entire structure has rotated. It has undergone a rigid body deformation. So that means that the effect of settlements is not there. These elements will not develop any additional force because of this settlement of the right hand side support. So whatever forces that we calculated earlier, that is tension 100, compression 100, tension 50, they will still be the same. That I am not doing here, but if you use these displacements and calculate the element forces, you will get the same forces that you got earlier. So I think that's the last slide. So I think that's the end of this lecture, and if you have any questions, please send an email to profkrg@gmail.com. And what I suggest is, please take a pen and paper and go through this entire this differentiation, because it's a bit messy, and when you see it on the screen it might seem bewildering, it might seem complicated, but then it's so simple, because it's simple differentiation with respect to different quantities d1, d2, d3. If you do it by hand on pen and paper, then you will easily understand. Okay. So that's the thing, and then we will continue further with other mathematical methods that are applicable for our equilibrium equations. So okay, thank you very much.